So let's now have a quick summary of how we derived the generalized delta rule, and also look at some pseudocode which would actually implement it for a two-layer network. So the first thing we need to do then is derive the error gradient for weights in the output layer in W2. So we need to calculate dE dW2. So how do we do this? Well, first of all, we write down the error. And we're doing this again from a sample by sample basis. So this is for one input vector and one output. We calculate the error as the difference between target and the output prediction. We square that, and we've got a factor of a half, which is arbitrary here. So let's split this up, because we need to use the chain rule. So we're going to say the term inside the square is target take away output, and that means that the error for that sample is a half u squared. So what we really care about is dE dW2. So we can split that up using the intermediate variable u that we've just defined, using the chain rule. So we can calculate dE dW2 as dE du dW2. Right, that's quite easy. And it's quite obvious that if we differentiate the u term with respect to W2, we get the du dW2 term equals minus do dW2, basically because the first term here, the t is a constant with respect to W2, so that disappears, and the output O is dependent on W2, so we need to work out what that derivative is going to be in a second when we actually expand out where the term O comes from. So basically we can put that first part of the chain rule into the expression that we have here for dE dW2, and now we've got the terms dE du do dW2 in there. Now do dW2, basically that's how the output changes with respect to W2, and we know that this goes via basically a linear combination of the inputs to that stage, and then it goes through a sigmoid to get to the output. So we can break it up in terms of an intermediate variable, which is representing the linear stage between input and output. Right. So let's expand that do dW2 term in this way using the chain rule, and we can write it down here like that. Now we know that the output basically is this non-linear function of the linear component net3, which comes from the linear combination of its input. And all we're going to do to start with is just write down what this differential is, do d net3, just in terms of f prime net3, and then we'll have to obviously put in that expression a little bit later on, but we've already put that in now, so we've already got this do d net3 term substituted with f prime net3. Now we can start carrying on evaluating the expression. So we know I think we're gonna look at now at the dE du, right? We're gonna sort that term out. We know that E equals half u squared, so u equals t minus O, the output. Therefore dE du is just u, which is basically target takeaway output. So we also know at the output that the derivative of the sigmoid is given by output multiplied by 1 minus output. We derived that a couple of times. We also know that net 3 is given by, so we know this is now tackling this derivative of the net 3 with respect to W2 term, this one here. We know that net 3, that's the network linear part of the network, and the output is given by its input multiplied by its weight matrix, so that's going to be W2 times A2, and if we differentiate that with respect to W2, we know that that's just going to go to A2 transpose. So look back how we basically did the differentiation last time, and look back at the first principles if you want to know why it changes to a transpose. Basically the result has got to be of the same form as the matrix for W2. If we stick all those together, so we just substitute all of these parts now, this goes in here, this goes in here, this goes in here, we end up with the expression dE dW2 equals minus target takeaway output multiplied by output multiplied by 1 minus output multiplied by the transpose of the activation from the lower level coming in, which is A2 transpose. And that basically gives us the gradient of the error with respect to the weights in the upper part of the network, the weights W2. So we can use that then to do gradient descent. Now the tricky bit is deriving the error gradient with respect to the weights in the first layer, right? So that's dE dW1 that we want. So again, we plough through the chain rule. Most of this first bit's the same again. So we've got the error again. Target value take away the predicted output squared, scaled by a half, which is arbitrary. Let's write down again an intermediate variable because this is a function of a function. U equals target takeaway output. Error is a half U squared. So let's break up this then into this intermediate stage and use the chain rule. So dE dW1 equals dE du multiplied by du dW1. Okay, and just like we did last time, we can evaluate du dW1. Last time it was du dW2. First term is a constant with respect to W1, so it disappears. Second term is going to depend on W1, so we can't just ignore the fact. So we're just going to first of all write it down as we have to take the derivative of output with respect to W1, and obviously there's a negative sign there. So we substitute in du dW1 into our expression here, and we're getting slowly towards the solution. So what can we actually do now? Let's tackle the dW1 term. So again, this is how the output is affected by changes in the weights in the first layer, and we know that there's an intermediate just before you get to the output, the final output. There's an intermediate linear part again. We had that last time. So what we can do is we can put the intermediate variable net3. We take that into account. So we calculate do dnet3 dw1 using the chain rule. So substituting this expression do dw1 into this expression here, we expand it out, it gets a bit bigger. Again, we know that the output is a function of net3, just like it was before, a nonlinear function, and it's going to be a sigmoid. We're just going to write it down again, derivative of do dd net3 as f prime net3. Again, we'll pop in the values that we need to in a second. So that's this term taken care of. We've substituted in there. Again, using the chain rule again, what we're going to do is we're going to now attack term dnet3 dw1, and in this case we notice that the output net3 basically has an intermediate variable below it, which is in terms of the activation from the lower level. So in other words, the linear output of the upper level has as an input the activations from the lower level. That's what A2 is. So we can use A2 as an intermediate variable. So we calculate d net3 dA2 dA2 dW1 in order to evaluate this differential using the chain rule. So let's substitute this expression into this term here. Then we've got to tackle once more breaking this down. So let's have a look at dA2 dW1, and this is again going to be broken down into the fact that this is an activation after the sigmoid. So what we can say is, well, actually there's an intermediate variable as well. Basically it's going to be the linear part in fact of the lower level network, which is going to be net2. So let's use that intermediate variable. So we're going to break down this using the chain rule into dA2, dnet2, dnet2, dw1. So let's just first of all substitute this expression into what we have here for this dA2, dw1. In it goes there. And we carry on, right? Let's sort out the bits we can. So we've got the dA2, dnet2. So this is basically saying how does the output of the sigmoid on the first layer, how does it change with respect to the linear input of that? And basically that's just due to this sigmoid function. So we have to differentiate the sigmoid function. So dA2, dnet2 is just going to be f prime of net2. So let's put that term in here. We notice, incidentally, f prime of net3 and f prime of net2 are not the same thing because they obviously depend on the outputs at those stages, right? We'll sort that out in a sec. Right, so let's carry on sorting this out. It does get a bit tedious, but that's life. What term are we going to tackle now? So we've got the DEDU term that we've got to get rid of, right? So let's go and look at what E equals half U squared, and U equals target takeaway output. So U is, again, the intermediate variable. So that's really easy to calculate DEDU because that's, again, just like it's always been, T minus O. So we know in this case that the output f prime of net3, that's the output sigmoid. We've done that on the sigmoid network when we had just a single layer, and we know that the derivative of basically of this is going to be the output multiplied by 1 minus the output. And in this case, the overall output of the system is O, so it's O multiplied by 1 minus O. We know now, let's tackle the next part, which is going to be the dnet3, dA2, right? So basically this is looking at how the linear output of the output stage changes with respect to the activation coming in from the lower level. So net3 we know equals W2A2, right? So that's basically just saying that the output of the linear output of the top layer is just the weighted sum of the activations coming in from the layer below, and that's easy to differentiate with respect to A. So that's just basically, again, when we differentiate this expression, we end up with something which is transposed, right? So the W2 gets transposed, and that's all that remains. F net2, again in this case, this is the nonlinearity at the output of the hidden layer, right? So the output of that is the activation levels. So it's not the overall output of the network, which was O before, it's now A2. So for this particular derivative, we see that f prime of net2 is going to be its output take away 1 minus its output. So it's A2 multiplied by 1 minus A2. So the final bit is net2 with respect to W1, right? Derived with respect to W1. So we know what net2 is. The output, that's the output of the lower part of the network, the linear output, and that is just a weighted sum of the inputs, right? So that's net2 is W1 times X, where X is actually the input vector, and we know already how to differentiate that with respect to W1. We know that the W1 disappears and we end up with X transpose. So now we've got all the bits, we can just plug them all together, and what we find is we end up with a rather complicated long expression, but this is for the lower level. dW1 equals minus target value, overall target value, take away overall output value, multiplied by overall output value, multiplied by 1 minus overall output value, multiplied by the transpose of W2, multiplied by, right, this is the intermediate level output value, the intermediate network output activations, minus 1 take away the intermediate activation values, multiplied then by the transpose of the overall input to the network. So how can we use this code? Well, actually, the calculations aren't so bad, and because all it comes down to is gradient descent, it's just a question of initializing, first of all, weight matrix 1 and weight matrix 2, again, to realistic values. Lots of things we'll say about that in a later lecture about how to do things appropriately. Very small values centered on 0, so some sort of small scaled version of something sampled using rand n would be a good way to go along. Then we've got an iterative loop because we want to do learning the weights by gradient descent in an iterative fashion. So what we're going to do, we're going to apply a pattern, we're going to look at the output, we're going to work out the gradient of the W2s, we're going to work out the gradient with respect to the W1s, and we're going to do gradient descent. So iterative loop, first thing we do, calculate the internal activations of layer 1. Right, so these are the intermediate activations from the first layer, which will feed into the second layer. Notice that we're going to need a bias term. This is the activations feeding in. We'll also have to have a bias term put in. We can assume that we have X to the overall network already having a bias term. You have to put it in when you're coding it though. And when we're calculating this activation, this is an element-wise sigmoid, right? So you need to do, if you implement this, you need to make sure that you actually do element-wise calculations, because it's basically for every value of going in here, we end up individually using this nonlinear function on them. So we're going to augment A2 to account for a bias term, so we give it a bias term, right? So we're going to A2 hat, we give it a bias term. Then we're going to calculate the output activations of layer 2. So this is really still the forward pass, right? And this gives us the overall output of the network. And again, this W2, A2, that's the linear part that we're calculating, the linear set of outputs. Again, if you've got multiple outputs, so if A2 hat, right, is a vector, then again this needs to be done element-wise. So now we calculate the output delta term, right? The delta term, don't forget that basically the gradient's going to be composed of the delta term and the input to that layer, right? That's how we work it out. So the delta term for the output network is minus target takeaway output of the network multiplied by output of the network multiplied by 1 minus output of the network. Now we have to calculate a back propagation term. We need to now calculate the lower level delta function, and this is then basically calculated by calculating the transpose of W2 multiplied by delta 3, which is the delta term we have here, but then we multiply it by also the activation coming out of the first layer multiplied by 1 minus the activation. And in this particular example here, right, W2 and A2 are not augmented, right? So we only want to back propagate values for basically we only need values which are actually correspond to outputs at that level. We're then going to calculate the gradient with respect to W1 overall, and like I said, the way it always works with this, we have a delta term for that layer multiplied by a transpose of the input to that layer. That's always the way it is. So dW1 is delta 2 times X transpose. So this is the lower level weights. The input to the lower level is X. So this is then the delta 2 term multiplied by the transpose of that input. And then we do the same thing for calculating the gradient of the error with respect to the weights in the second layer. And this is the easier one. But basically, this is then just given by delta 3, which is the output delta term, multiplied by basically the augmented inputs going into it transposed. And then very simply, we update the weights just by moving down the gradient. So we just say all the weights are what they were before, but we take away a scaled version of the gradient from them. So alpha here is going to be a single value, which is it's going to be a scalar. So we have to multiply alpha by every term in this matrix, and then take it away from W1 in order to get the next W1. And similarly, we do the same thing for W2. So we basically take away a scaled version of the gradient of the error with respect to W2. So alpha is known as the learning rate, and that's normally quite a tiny little number. In some schemes it's adaptive as well, so something to think about. We'll discuss later on. And that's the end of the loop, and we have some kind of termination condition, of course. So you'd basically look maybe when the gradient's going almost to zero, or you might just decide that you're going to have an emergency. It's done enough, it's taken too long. We run it for so many iterations and see what it's doing. Another thing you can also do, of course, is always calculate the error, so you can get an idea of what the error is as time proceeds, and that's really a good thing to do, to plot things out to see how the error is coming down.